Hi guys, it's Mr. T again, and I'm going to do a little short video, series of short videos on our polynomial packet. Give you a few examples along the way. I think the introduction I did with polynomials in general is pretty good, but just give you a few more hints as we go through this packet. So let's get to it. So here we are. First page of the packet is coming from our current textbook in section 2, and so the first thing it's asking us here is identify the function graphed as odd or even degree. Okay, and what we see here in this very first one is that both of the arrows are down, so that has to be even because it's a quadratic or to the second power. This one has 3 turns, and they're both well, we're really worried about the endpoints here. They're both up. Okay, so this is also an even degree, has to be an even degree. And this one's down and this one is up on the endpoint, so it has to be odd, because on evens they're either both up and both down, or on odds there's like one up and one down, like that. So that's one thing we know for sure. Positive or negative leading coefficient. Okay, so that's the next piece of it. So if we were to write the equation out in front of it, would it be a positive leading coefficient or a negative leading coefficient? Well, both of these are down, so this is an even down. Okay, both of these are up in points, and so that's an even up. Okay, and so that would be a positive in front, even up. Whoops, positive. Sorry. And so, and this is going, if you connect from here up to there, okay, I may actually do this one here for you. Okay, and we see a little bit going on here. You see, that's a positive slope, doesn't it? So this is odd and a positive slope. Okay, this is interesting. See if I can keep myself right there. Okay. All right. So that should get you started on that piece of it. Now let's go a couple more here. Okay, now it says use a graphing calculator to determine the number of turning points and the number and type of either global or local maximum or minimum values. Okay, well, let's go up here and talk about these guys first, because so what we have here on this first one here, that has one turning point, okay, and it's right here at the top, and so that makes it a maximum. And since there's no point taller than that, we're going to call it global, or another word that we use is absolutely. So there's absolutely nothing taller than that. Okay, even my wonderful tree here, on my virtual beach, it's the absolutely tallest point on my graph. Okay, absolute or global. Okay, so that's a global maximum. Now here on this one example, we got a minimum, and then we have a maximum, and then a minimum. Okay, so this is the first time when we've come to across this where you have multiples of them, because up to now we've only dealt with parabolas. So this is the absolute minimum point. That's the absolutely bottom part there. So we call that a global, or another word, absolute minimum. Okay. Now this is also a minimum up here, is it not? Okay. And it is a relative or local minimum. So what does that mean? It means, well, in the local neighborhood, it is the smallest spot, right? It's the lowest place. Or in it, relatively speaking, right? This is the minimum, okay? And that's the same idea here with this guy. It is a local maximum, because if you notice, there are definitely things taller than it. Absolutely, they go up higher. So for in the area that is still a relative or not a global, or relative or local maximum. Okay. And something we take note of here is over here. Now this is an odd degree, and this is a maximum, but it's a local maximum, because yeah, there's definitely stuff that's going to be taller later. Okay. And this is a minimum, and it's a local or relative minimum, because this definitely got some stuff going to go lower later, right? And so what we also take note of is odds never have globals. Can't, because you got this down arrow and up arrow. You can't have global max or mins with an odd degree. You can only have globals is if you have an even degree. Okay. All right. Let's see here. So let's go ahead and look at this particular one. Oh, I'm sorry, we didn't talk about turning points. That's definitely one turning point. This is 1, 2, 3 turning points. Okay. And this has got 2 turning points. Now, previously, I don't know if I said the number. Okay, no. This is a second degree or quadratic. You notice it's a second degree and it has what? 1 turning point. So 2 minus 1 is, oh, isn't that interesting? It turns out that that's going to happen often. Okay. This is a fourth degree and it has 3 turning points. So it's a fourth degree. It has to be even. And it can't be 2, right? Because, well, that's not a quadratic. So we got to be even. So we got to go up to 4. And it has 3 turning points. So fourth degree, 3 turning points. Fourth degree, 3 turning points. Now, does it have to be a fourth degree, does it have to have 3 turning points? No, there are examples that have less than that, like the parent function, as a matter of fact. But the most turning points that a fourth degree can have is 3. So just take the degree minus 1, and that'll give you the maximum number of turning points, okay? And then we got this third degree here with 2 turning points, okay? All right, so let's go ahead and look at this guy here because it said look global and local and all that kind of stuff. So I'm going to do a quick look at my graph here. I've already got it plugged in, and here it is. And so, all right, it's got a local maximum and a local minimum and 2 turning points. So that's easy enough to do there. Okay, so we can continue that process with those guys there. Now, this one says graph the function and state the end behavior. But I tell you what, we might graph it in a minute, but I don't really care. We're going to sketch this guy using our graph paper, and we already kind of know how to do that. So I want you to go a little bit further down for me. There we go. Can I not get all my questions answered? There we go. I can get it all in now, I think. All right. Bam. Okay. So, I'll get that double vision out of here again. Where should we start? Well, let's first start with the zeros, okay? The zeros. And so if x minus 1 is my factor, what can I plug in to make it equal to 0? Positive 1. So it's going to cross the x-axis at 1, okay? And this is x plus 3. That's my factor. And so the 0, what can I plug in to make it equal to 0? A negative 3, right? Because remember, when we're solving these kind of polynomials, we're going to put a 0 here. And so we're always looking for what can I plug in to make it equal 0? Because that's what does y equal on the axis? Y is always 0. Okay, so that's definitely my 2 options for my x-intercepts. Something else we notice here is we have this square here. And so the official term is when our graph comes to this point here at positive 1, it's going to be tangent. I call it a bounce, okay? And so when I do that, to help me remember when I go to graph this thing, I'm going to highlight this guy a little bit. So when I go to graph it, it'll help me remember that. Then, okay, and this, now we got a negative. Hold on a second. Let's make a note of something. What is the degree of this function? Well, if I was to multiply all this back out, I would eventually get a highest exponent of 3. And so the degree is 3, 2, and 1. So when it's in factored or intercept form, you can add the exponents, and that'll give you your degree. Okay, so it's an odd degree, and then we have a what? A negative leading coefficient. So what I know to be true is it's going to be going downhill. So it's going to be pointing up on this side, and to the right of this point here, I'm going to put a downhill. Okay, because it's negative and odd, it has to have these ending behaviors. Okay, so I've got my zeros in place. I got my end behaviors set up. I noted that this is going to be a bounce because there's a square there. Okay, so it might be better if I erase that and just highlight it instead. There we go, and now they'll match. All right, so I think we're ready to actually do our sketch. Okay, so I'm going to start here, head towards this point here, and I got to ask myself, am I going to go through or bounce? Well, that's a bounce, and it's not, and so I'm going to go through it. And well, where's my next point? Oh, it's up there, so I need to give it a turn around, head towards this one. Now this means I'm going to bounce off or tangent, and boom, there we go. Now, if I stick it in the calculator, will it go exactly like those turns? Probably not, but it's going to be something really similar to that, and it'll definitely start up here, go through this point, and bounce off there and go down. Where exactly the turns will be, I don't know, but that's not really our issue here. And so now let's talk about end behaviors. How do we always say end behaviors? So this is how we always talk about end behaviors. We first of all start by saying x approaches positive infinity. Also, and x's only go left and right. So that means right. And then we have x approaches negative infinity. And again, x's only go left and right, and so negative infinity means left. Okay, so that's always how we start this guy off. And then we're going to go f of x, also known as y, f of x. Okay, so here we go. Here, as we go to the right, and again, we're talking about the end behavior. I don't care about the squiggly stuff in the middle. So that blue arrow is what I'm talking about. As we go to the right, y, is it going up or down? It's going down. So I'm going to put negative infinity. Okay. And this means left. So that means that blue arrow up there. As I go to the left, my graph is going up. So the y is approaching positive infinity. That's how we do those guys. So that gets you set up. Well, I guess we can go ahead and do a couple more of these. The x-intercepts, well, that would be the zeros, also known as the zeros, right? -3 and 1. And above the x-axis, well, where is it above the x-axis? Well, it's above the x-axis from here up there. So we're going to say that is negative infinity less than x less than -3. Okay. Or we could say what? What's another way we could write that? Is negative infinity, comma, -3. And so that's interval notation. So we could write it in either way. Okay. Is there any other sections above the axis? No. Okay. And why are we using x for specifically to describe it? Because we already know what the y is doing. Because what is the y doing? It's being above, right? So we already know what y is doing. We're trying to figure out what x is doing while y is jumping around above the axis. Okay. So we're talking about where is that? Where's all the y's above the axis? Oh, it's over there where the x's are -3 or smaller. Okay. That's what we're trying to figure out. So now it says what happens when the x's are below the axis. So, okay, below the x-axis, excuse me. So when the y's are below the x-axis. So where is that at? Well, some of you might say from -3 all the way to positive infinity, but we forgot something. This spot, 1, is that below the axis? No, it's actually on it. So you can't be on and below at the same time. So we're going to have to write this in two separate statements, okay? So you're going to say from -3 less than x less than 1. And then you're also going to have to say from 1 to positive infinity. And now or you could say what? For this guy, you could say x is greater than 1. That's another way you could say that. All right, I think we got that front page done. The back page is just pretty much the same exact thing. There is one slight little difference that I want to talk to you about on the back page, okay? So you got the same basic questions, but you do have some more twists and turns in there. So on number 4 here, we do have a cube in here. So I do want to look at that graph just a moment, okay? So I'm going to come here to my y equals, and I'm going to turn off my first graph. come down. If I can get to that, there we go, and hit enter and see how now it's highlighted, and I hit my graph now, and voila. All right, so we see on this guy, it's coming up through the -2, has one turning point, and then you might think, is this a turning point? No, it is not. It is not a turning point. Okay, a turning point has to change direction. So what's happening with this guy is you're coming down, it's sliding to the right, and it starts to act like it's going to do U-turn, and then it changes its mind and keeps on going down. So I call it a swerve, right? Point of inflection, I think it's probably the proper term, but a swerve, because you're kind of swerving a little bit, but you're not turning. So this only has one turning point, but it's still to the fourth power, because this is because x cubed, that's where you get your swerves, if you remember from previous video in practice, right? So there's your swerve. So hope that was a helpful and to get you started on the polynomial packet.